Thank you very much. I'm very, very happy to be here. Thank you for coming on Saturday. So I'm going to speak about something very elementary. The beginning will be extremely elementary. By the end, it will be less elementary, but still elementary. So the starting point is a very well-known fact. Consider compact, say complex manifold of dimension n. Then we know this statement is essential for real manifolds, but let me go into the complex setting. Then we know theorem, the only characteristic of n is the total index, Poincaré-Hopf index of a vector field in n, or any continuous vector field on n with finitely many singularities. So the only characteristic of n is the total Poincaré-Hopf index of a vector field, any vector field on n with finitely many singularities, and this equals also the top Schoen class of n evaluated on the fundamental cycle. Okay, so that's very well known, very elementary. That's the starting point. So the question I want to explore, and a lot is known, is what happens if we consider V embedded in n singular variety. I want to think of this, but for singular varieties. Okay, so this is the question I want to explore. And then the first question is, what is or should be the index of a vector field on a singular variety, and what is or should be the Schoen class of the singular variety, and how these relate to your characteristic. Okay, those very elementary questions. A lot is known, and there are some things which are not so well known. So, two cases I want to consider. One, V is a hypersurface in n, or more generally, a complete intersection. Everything is essentially the same. To general case. And just for simplicity, and this is already not so simple, assume V has isolated singularities. I will mention something about the general case, removing this hypothesis also. But let me stay with that. Okay, so let me speak first about the first question, indices.
Excuse me?
Yes.
So could you,
use only this word?
Yes.
Okay,
So,
yeah, sure. Thank you. Okay, so first, let me say a few words about indices of vector fields. On singular varieties. Okay, and let me take V embedded in M at hypersurface. P in V, an isolated singularity. Okay, and so let me take the classical picture. P. This is a local question. And suppose we have a vector field continuous for the moment. At some point, I will look at holomorphic vector fields. For the moment, just continuous. And suppose it's what does continuous mean? Suppose you have a continuous vector field in the ambient space, which on V is tangent to V. We have a singularity at the point. Okay, and take the restriction to the singular variety. So we want to look at that. Now, what is the index? Well, it depends on what you want, what properties you want. The Poincaré index has many properties. When you go to the singular variety, you cannot have all of them at the same time. So it depends on what you want. And there are several notions. The first considering this kind of problems was in the early 60s. Marilyn Schwartz. What she was actually interested, I will come later, in chain classes for singular varieties. And she didn't want to consider vector fields in general. She just considered one particular type of vector fields that what she was needing. And in the case of isolated singularities, the only vector fields that she would consider were the radial vector fields. That means that in a neighborhood of the singular point, they would be escaping from every small ball. Okay, so in that case, her index was 1. So it was interesting for what she wanted, not from this viewpoint, and that was extended. So in the 1994 by Henry King and David Trotman. Now this paper has a peculiar history. I think it's probably in the Guinness Book of Records because it was never published until 2017. So if you complain because your paper is taking too long to be published, it can be worse, okay? So then in the meantime, in the 1997, I think, I came with Alberto, with a colleague in Mexico, Marcelo Aguilar, Berkowski, and myself. And at more or less the same time, Eveling and Hussein Seade, we all came with more or less the same definitions, different names, and so on. And,
This Trotman guy is from Princeton.
sorry?
This Trotman guy is from Princeton.
No, he's David Trotman. He's in Marseille, in France. And then we all came with what is known today as the radial index. A very simple definition, especially in the isolated case. This definition actually applies for real analytic varieties with arbitrary singular locus. Just the definition is technically more complicated, but the idea is very simple. The idea is as follows. We have our variety, assumes isolated singularity for simplicity, And we know that every real or complex analytic space has a local conical structure around each singular point. Which means that in this case we have P. Suppose since this is local, you are in some CM. Then if you take the intersection with every sufficiently small sphere centered at the singular point, this intersection is transversal. Okay, this intersection is what is called the link of V, which is V intersected with a sufficiently small sphere. Now, away from the singular point, this is a smooth manifold. You have transverse intersection of two manifolds. The link is a manifold. Okay, and the local conical structure tells you that the way V looks inside the ball is just the cone over this manifold. Or in other words, V looks like taking this intersection and then the same, making smaller and smaller and smaller and smaller links until you degenerate into a point. Okay, that's the local conical structure of analytic sets. Now, you can consider here the vector field in question, which is non-singular on the link. It has an associated singularity here. And now you take a smaller link, and here you put the radial outwards pointing vector. By definition, this has index 1. Why 1? Several reasons. One reason is because 1 is the only characteristic of a point. Also because you can, if you extend it to the ambient space in a natural way, it is radial in the ambient space, and the local Poincaré-Hopf index of the radial vector field in the ambient space is 1. Okay, so for this one, the radial index is 1. For this one, now look at this cylinder. This is a smooth manifold with boundary, 2 copies of the link. This vector field can be extended in many ways to the interior, with finitely many singularities in the interior. You count them, and the number you get is independent of how you extend it. Then you define the radial index of this one to be 1 plus the total Poincaré-Hopf index in this manifold. Okay, that's the radial index, very elementary definition, very natural. And then with this definition, it is an exercise to show that the V in M is compact. Then you can define the notion of the total index in the obvious way. If you have a vector field on V with isolated singularities, you will have singularities of the vector field at the singular points of V, and possibly some other singularities in the smooth part. So at the singular point, you take the radial index. At the smooth points, you take the usual Poincaré-Hopf index. You take the sum, and you call that the total radial index. Then it's an exercise to show that that number, the total radial index of a vector field, is independent of the vector field, and it equals the Euler characteristic. It's very easy. That's one definition. As I said, it has several properties of the Poincaré-Hopf index. It doesn't have other properties. There's a somehow previously defined index. This is called the Gsb index. That was defined by myself in the early 1980s for surfaces, for vector fields and surfaces, complex surfaces, and then by Gomez-Mont, myself, and Verhofsky in general. It was published in late 1980s. We defined it. It appeared in Mathematician Allen in 1991. So it was before the other one in general. And For the other definition, it is for any real or complex analytic space and for arbitrary singular locus. This one is more delicate. We do need a hypersurface or complete intersection. And for this definition, we need isolated singularity. There are interpretations, I'll come to that later. But for this definition, we need to assume a hypersurface with an isolated singularity. And the definition is very simple. Suppose locally V is defined as the zero locus of a holomorphic map J. Okay, so you have F locally from C, let me say n plus 1 into C, taking P, let me say to the origin, and we're going to isolate the critical point at F. Okay, then you have this vector field, and in the spirit of the Poincaré-Hopf index, you could say we restrict the vector field V to the link. It is non-zero there. We divide it by its norm. We have a map from V into the unit sphere in the ambient space. But this is too highly connected for this dimension. So every such map is null homotopic, and the index will be 1 for every vector field, not very interesting. Sorry, 0 for every vector field. So it will be, but then we remember that this is defined by one function. And we have the gradient, conjugate gradient vector field that you can divide by its norm. And you have a unitary two-frame. Okay? And then we have now in the correct dimensions. These maps from this, now we're going to the, now we're going to the Stiefel manifold of two frames in C2n plus 1. And these maps are classified by an integer. You have as many as an integer. So you have a well-defined degree. Okay. So you define the Gsb index of this vector field to be the degree of this map. Okay. And then it's an exercise to show that it has a very natural, nice geometric interpretation as follows. Take the so-called Milnor fiber of F. That means you take the local non-critical level of the function. Here we have a critical point, you are at the critical level. Take the non-critical level. The portion of this within a small ball. Then once you fix a Milnor sphere, that means a sphere where you have a conical structure, then you take a non-critical level sufficiently close to the critical level, sufficiently close with respect to the Milnor ball. What sits inside, this is F minus 1 of T intersected with this ball, not with the sphere, but within the ball, the solid ball, for T sufficiently small with respect to epsilon. This is called the Milnor fiber. Okay. Now it's an exercise to see that this vector field you have on V can be is isotopic to a vector field on the boundary of the Milnor fiber without singularities. Now you have a manifold with boundary, a vector field on the boundary, you extend it to the interior with finitely many singularities, you count the Poincaré-Hopf index, and the number you get is exactly this one. Okay, so this gives you a nice geometric interpretation. And then you have this index. And how does this relate to the Euler characteristic? That's an easy exercise in topology to show the following. theorem. If you have V embedded in M compact with isolated singularities and codimension 1, so we have a hypersurface in the compact manifold, and then V vector field on M on V with isolated singularities, then I forgot to state something, so let me state it here. I will put everything together here. With isolated singularity, let me say x1 up to xr. These are the singularities. These are the singularities of V, not of the vector field. X1 up to xr. So the vector field will be singular at these points and possibly at some small points. Okay? Then two statements. The first one is local. We have the Gsb index of the vector field at xi relative to b, and then we have also the radial index of vector field at the point relative to v, and this difference is -1 to the n times the local Milnor number, where mu I is the local Milnor number. Let me remind what this is. We have the Milnor, at each isolated singularity we have the Milnor fiber. This is well known to have the homotopy type of a bouquet of spheres of middle dimension. How many spheres? Some positive number, which can be evaluated as by definition that is the Milnor number, mu I. So it's the Milnor number at the point pi or xi, let me say, using that notation. And this is by definition the number of spheres or the rank or the middle homology group of the Milnor fiber. And this can be evaluated algebraically as the dimension over C of the local ring of functions in the ambient space at the point xi divided by the Jacobian ideal. Okay, so we have this algebra, we take its dimension, and that is the local Milnor number. Okay, so this has a very nice algebraic definition, and topological is just the number of spheres in the middle homology of this. And actually, one knows more, or later, one knows that the Milnor fiber is actually diffeomorphic to a manifold obtained by taking a solid ball of the correct dimension, and then attaching to it handles of middle Morse index. How many handles? As many as the Milnor number. Okay, so this gives you the diffeomorphism type of the Milnor fiber, this number. And then if you take these two indices, the difference is independent of the choice of the vector field, and it's always given by the Milnor number up to sign. Okay, and the second is a global statement. The total Gsb index of the vector field is the Euler characteristic of this fellow. Who is that? This is taking, you have now you have the variety, which is compact. This is V. And what you do is, at each singular point, you take a conical neighborhood, you chop it off, and you replace it by a local middle fiber. So you take a C-infinity smoothing of the singularity. Okay, and that is this manifold now, and then the total Gsb index on V is just the other characteristic of this smoothing. And then, as a corollary, you get that the difference minus the radial index is independent of the vector field and is just the sum of the local Milnor numbers. Very elementary. Okay, so now let me move to chain classes. Chain classes. Let me recall first. E is a complex vector bundle over B, a nice simplicial cell complex. And here a complex vector bundle, I don't mean holomorphic vector bundle. I just mean that the fiber is a complex vector bundle and the gluing maps are in GL and C. Then, by definition, let me say this is a complex vector bundle of rank or fiber dimension K over a simplicial complex, let me say dimension 2n, or let me say so over a singular variety already. That's what I'm going to be using of complex dimension n. Okay, so just by definition, the chain classes have many. This setting, if this were holomorphic, you will have many possible definitions. Even in the topological case, you have several possible definitions. Let me give one very elementary, which is by the obstruction theory, classical obstruction theory, which is take a triangulation of E, of B, the base, or cell decomposition, then you can always construct a section. Let me assume K is less or equal to N. I can always construct a section of E over the skeleton of dimension. I'm going to get confused. Sorry. This is very, but I don't want to get confused in the dimensions. Let me take, I apologize. We'll do it in general in a moment, but I don't want to get confused. I don't want to get confused and then get you confused. Let me take the fiber dimension is the same as the base dimension. Sorry, incomplex. Then can always construct a skeleton over the skeleton of dimension, real dimension 2n minus 1. Okay, so you have the variety, you have you have a triangulation, and then for each face of top dimension, you can always construct a section over the boundary, and then when you want to extend it to the interior, you have a local obstruction for each one, and then you can define a cocycle in the natural way, which is you take sum over all the triangles, sigma of dimension to n, and to each one you attach a number, which is an index, which is just like the Poincaré-Hopf index, the local obstruction for extending the vector field, the section to the interior of the cell. Okay? You get a cycle, and that is by definition the top dimensional Chern class. Okay. Now, if this is less or equal, less, if it is equal, yeah, we said, if it is less than n, then you can always do the same up to dimension 2n minus 2k plus 1. Let me check if this is correct. If k I think so. No, so sorry. You can always go to the up to dimension 2k minus 1. This is just by homotopy theory. And then when you want to go to cells of dimension 2k, for each one, you have a local map. The section gives you a map from the boundary, which would be a cell of dimension 2k minus 1. You have locally a map from there to the fiber, which is a 2k minus 1 dimensional sphere that may or may not be homotopic to 0. You have a local obstruction, and you get an index, and you have the top Chern class of this. Okay. Now, more generally, if you have a complex vector bundle, you may try to construct not one section, but a certain number of sections. Okay? 2 sections, linearly independent. They require 3 sections. Okay. So just homotopy theory tells you in the same way that you can always, if you want to construct so for simplicity, let me assume this is rank n. And now we want to construct k. It's okay. Rank R. Now we want to construct k sections with k less or equal to R, which is less or equal to n. Then it's easy to see just by homotopy theory that you can do it up to the skeleton of dimension 2k to R minus 2k plus 1. So you can do it, we always can construct these many sections. But then when you want to go to the next skeleton, you meet an obstruction, and that is by definition the corresponding Chern class C R minus k plus 1 of E, which lives in the cohomology of dimension 2R minus k plus 1 of the base. Okay, so those are the classical. So whenever you have a vector bundle over a variety, this is the classical. These are the classical Chern classes. Now, if these were a manifold, by definition, the Chern classes of the manifold are the classes defined in this way, or the tangent bundle. But if this is if you have singularities, then what is the tangent bundle? So for each reasonable definition you have of a tangent bundle of something which plays the role of the tangent bundle, then you have a type of Chern classes. So there are many extensions, and each extension of the notion of Chern classes to singular varieties has some properties. Now, let me speak about two. Okay, so what has the Schwartz classes? These were defined in 1965. And you take V, complex analytic, variety, in a complex manifold M. Okay, now take Whitney stratification for M adapted to V, so V is union of strata. And I'll take triangulation adapted to the stratification. And I'll take, let me say K, and take D, the dual cell decomposition. This is very elementary, I will not go into details for time, but this is a very nice cell decomposition of M, which has the property that every cell is transversal to every stratum in V. Okay? So if you have a cell, its codimension in the ambient space is the same as taking the intersection with V and its codimension in V. And this is what she used. And now, instead of, for the usual Chern classes, you take any frame and any triangulation, and the class you get is independent of the choices. Here, you take stratified frames. That means at each point, all vector fields or all sections of your bundle. In this case, you take the tangent bundle of M and you restrict it to V. But you take stratified frames. That means at each point, you don't take arbitrary vector fields on M, but vector fields which are tangent to V, tangent to the stratum where you are. Okay, so you take stratified vector fields and you work with this cell decomposition. And then you do the same theory as for Chern classes. You have to count indices appropriately, and what you get are the Schwartz classes. Okay, and naively, so you do the same, and you do that, but what you get, you get the Schwartz classes, but these are elements in H star of M relative to V. Let me explain what is the idea. You have the singular variety. Let me take a neighborhood of the variety. So you have the variety V, and let me take a neighborhood. Now, observe that just by excision, the homology of this is the same as the homology of taking the neighborhood and then the neighborhood minus V. Okay? So look at this. U is a nice, regular neighborhood of the singular variety. This is an open set in a complex manifold. This is a complex manifold. So you have the tangent bundle of U. Its Chern classes of this live in the cohomology of U. Yeah, by definition. But then you have the cohomology of U relative to this. Okay, so you have this Chromology sequence. So whenever you have classes here, you can look at liftings here. You may or may not have liftings, and you can have many different liftings. Okay? So the Schwarz classes are a particular, very nice, very canonical lifting of the usual chain classes of this guy here. Sorry, of the usual chain classes here. They live here. They give you a very natural lifting here. Those are by definition the Schwarz classes. Okay? But now, so far you say you want something of V, and now you are in this strange homology. Yes, Alexander duality tells you that this is the same isomorphic to the homology of V. Okay? So they naturally live in the homology of V. If V were smooth, this would be the Poincaré duals of the usual chain classes, which live in the homology. Okay? And those were defined by Marilyn Schwarz in the 60s. Then a few years later, the Ligne and Grothendieck conjecture that there would exist for every complex variety, there should exist homology chain classes satisfying certain properties. Then McPherson proved the existence of those classes. And then later, Bracelet and Schwarz proved that the Schwarz classes, which by her were considered here, when you came here, those were the McPherson classes. Okay, so this theory fits together very nicely. And now, coming back to what I was talking before, one has a very, let me say, theorem. It's very elementary. In this case, from this construction, is that if you have a BV embedded M compact, and you have a vector field with, let me say, compact with isolated singularities, and you have a vector field on V with isolated singularities, then the total radial index is the other characteristic of V independent of the vector field. And sorry, this I had already said before, sorry. This is by definition the top Schwarz-McPherson class of V, which I do not do like this, but cap with this. So when you go to when you do this, you go to degree 0. Okay? Now, about the other index I have defined, it is much simpler, the definition in the surface case.
Can you define these classes using the resolution?
Sorry?
Can you define these classes using resolution?
You have properties, but obviously, when you look at the resolution, it depends on which resolution. Yeah, but this has very nice functorial properties, so you can recover a lot. Yeah.
But there is a couple of things. The McPherson definition that coincides with the Schwarz definition uses a Nash blow-up.
Yeah.
Additionally, Bernardo, Tommaso de Fernex,
and
I modified a little bit this definition so that it could be a K invariant. You have this Kawamata kind of transformation, then you would get the same. But it's not the Schwarz-McPherson, it's what we call the stringy chain classes. So you have to take into account the twisted sectors of the singularity, and then it becomes a very good birational chain class.
Yeah. Yeah. So let me say, this definition I gave, I like it because it's very geometric and intuitive, and you can taste what you're doing, but it's impossible to work with it. You cannot prove almost anything with it. If you want to prove something, then you have to use McPherson's definition, and that's very powerful. So it is very nice because you have the two sides.
That's what you're saying doesn't depend on the
Well, one can make a precise statement, but it's a very good, it's a good birational correction of the. It's not a very good for birational geometry, but our correction, taking into account the twisted sector, so to speak, becomes a very good birational geometry chain class.
Let me come to another type, which are the Fulton classes. Now, let me take V in a complex manifold M, let me say defined by a regular holomorphic section of E, rank K less or equal to M bundle. Okay. So now look at the tangent bundle of M restricted to V, and look at E restricted to V. And you can consider this guy who is called the virtual tangent bundle of V. If V were smooth, this would essentially be the tangent bundle of V. Because this would be isomorphic to the normal bundle, and this would in principle be the tangent bundle. So the chain classes of this guy could be the chain classes of V. But what are the chain classes of a virtual bundle? Well, you take the total chain class of this guy, then you take the total chain class of this guy that lives in the cohomology of V, and that's in the cohomology ring. You take the inverse, and you take the product of the chain class of this times the chain class of the inverse, and that gives you, those are by definition the chain classes of the virtual bundle. Okay? So even in the singular case, you have this well-defined bundle, and you define the Fulton classes to be C star of this bundle, which is by definition the total chain class of the tangent bundle of M restricted to V times the total chain class of E restricted to V minus 1. That's by definition. So very simple definition, and actually very computable. Now, this has a very nice property that the way I define it, it is for complete intersections, defining this way. But this has an algebraic definition for compact varieties, and can be done for analytic, which algebraically is very nice. We know that this is essentially what is called the Seade class, the total Seade class. And those are defined. Yes, exactly. So this was the starting point for his definition. Okay? And so these are actually defined for every analytic variety in a complex manifold. Not with this definition, but using the Seade classes. Okay? But these are defined in full generality. Now, in this context, one has the following theorem. The n-dimensional Fulton class of V is the total Gsb index of a vector field on V. Okay? And then this implies that the Cn, the total Fulton-Johnson class minus the n-dimensional Schwarz-McPherson class, the difference is by definition, for what I said before, just the sum of the local, sorry, this is true in general, if V has isolated singularities, then this is the sum of the local Miller numbers. Okay? If the singularities are not isolated, you have a similar statement. The definition of the Gsb index doesn't apply. You have to use differential geometry, and there is what is called the, sorry, I forgot the name, the virtual index, which is defined by Chern-Weil theory using connections, and there's an extension of the Gsb index to this setting, and you have this is the same statement. Okay? But still using complete intersections. Now, in the last few minutes, just let me move. What if you have a variety, even with isolated singularities, which is not a complete intersection? Okay? Then, everything I said about the radial index and Schwarz-McPherson classes extends. That's in general. But this side, no, does not. Firstly, the definition of the Gsb index or the virtual index that I just mentioned, those are for complete intersections. But there's a very beautiful definition, very algebraic, which comes very much into this setting by Gomez-Mont of what he called the homological index. So let me take F from, everything is local, but just let me, for simplicity, holomorphic with isolated. No, sorry, no. This is general. Take V, P, normal, isolated singularity in some Cn. This has dimension, complex dimension n. Any codimension, any, just normal, isolated. Okay, now take this space of holomorphic n forms at P. And assume let V be a holomorphic vector field tangent to V with an isolated singularity at P. Now take the holomorphic n forms at V. You have a holomorphic vector field, you can take the contraction. And then you can show that this is the contraction invariant space, but you can show that it is well defined looking at the Kähler forms on V. So the contraction gives you a map into omega n minus 1 of V P. And then you contract again. Finally, you come to the holomorphic functions, and you go to 0. Okay. This is a complex. You can take, and it's easy to see that the homology groups of this complex are finite dimensional. But this is all Gomez-Mont. Okay, and then you he defined the homological index of V on V to be the sum of the dimension of the homology groups of this complex. Okay, with a minus 1 to the n, to the I. Okay, so you take the other characteristic of this complex, and that's a number, it's a finite number, you have to show, but this is not very difficult. And that number is by definition the homological index. That's defined always for all singularities, normal isolated, and holomorphic vector fields. Now, theorem of Gomez-Mont for hypersurfaces. And of Gomez-Mont with two other guys from Bodmer and Eveling for complete intersections is if V is a complete intersection, then the index, the homological index, coincides with the Gsb index for all vector fields. Okay, but this has the nice thing of being defined for every normal isolated singularity. And then an exercise. An exercise, a theorem, but the very easy theorem is if V has isolated normal singularities, then the total homological index of a vector field on V, of a holomorphic vector field on V, is independent of the vector field. Okay, that means that one has an invariant that one could call homological index of V. That's an invariant of the variety that does not depend on the choice of the vector field. Then the question is, what is it? I don't know. So my conjecture is that the total homological index of V is the Fulton class of this degree. Yeah, this is my conjecture. I believe that is true, and it is true for complete intersections. And this is essentially the same as asking who plays the role of the Milnor number at an isolated singularity which is not a complete intersection. So, and just to finish, let me say that here I consider all the time Cn, but you could consider also other Chern numbers. And Eveling and José and Seade observed that most of what I've said today extends for other Chern numbers. One has to use differential forms instead of vector fields, for reasons I want to explain. But then one can ask, what about other Chern numbers? And you get different invariants of algebraic varieties, analytic varieties. And the general philosophy behind this is there's a long history about Chern classes for singular varieties. So the question I was asking Ernesto before is, what can we say, or what information about the topology and geometry of singular varieties is encoded in the different notions of Chern classes? That's an area about which very little is known, and I think a lot is to be known. And I finish here.
Thank you very much. So, is there any question?
How many examples have you checked for this conjecture?
Very few, very few. It's very hard. It's very hard.
I guess stupid question. So in this definitions, you use vector field. It was a local. Is it obvious that you can always
No, it's not obvious, but it's true. So, no, but it's not obvious. So it's a theorem, it's an observational theorem by Gomez-Mond long ago with Bonatti, that if you have any complex normal singularity, you have infinitely many vector fields with an isolated singularity. And for example, one question for me is interesting. If the ambient space were Cn, we know that the Poincare-Hopf index is greater or equal to 0. And if there's a singularity of the vector field, then the Poincare-Hopf index is at least 1. So there's some, okay? For holomorph, now if this is arbitrary, one can have examples where the homological index is negative. But it cannot be arbitrarily negative. One can show that for every V, there's a minimum homological index, a smallest homological index, and the holomorphic vector fields with that index are dense. What is that number? So in other words, what would you call a generic vector field on an isolated singularity germ? What would be to be generic? One definition would be to have this minimum index, but we don't know what that is.
Another question here. So you mentioned a lot of the singularities is locally complete intersection and everything responds fine. But there's another class of singularities, like motion singularities. Motion singularities.
Yeah. That's a very good question, and I cannot say almost anything. All these things I know, once you are outside the complete intersection world, yeah, and the natural question is exactly what you say. Yeah. In fact, I was asking that yesterday, mentioning that yesterday to Ernesto. Yeah.
So this theorem which we raised by everything
Yes. So for hypersurfaces, long ago, Gomez-Mond proved that the Gsb index and the homological index coincide. But then 10 years later, they proved the same theorem for vector fields on complete intersection germs.
Okay.
So for this homological index, do you still have some description using the link of the singularity?
No. Yes and no. If it is a complete intersection, then it coincides with the Gsb index, and then it is defined using the link. But if not, then no. For the homological index, once you are away from the complete intersection case, nothing is known so far. And I think it would be very interesting to try to understand it.
Okay, if there is no other question, let's thank to the speaker.
Okay.